Here's a thought experiment. You're standing in a train station. A train passes by at half the speed of light. Someone on that train shines a flashlight forward. How fast is the light moving from your perspective? Common sense says the speed of light plus half the speed of light, 1.5 times the speed of light. Faster than light itself. That's how speeds work. You're on a train going 50 miles per hour. You throw a ball forward at 10 miles per hour. The ball is moving at 60 miles per hour relative to the ground. Basic physics. But that's not what happens with light. The light from the flashlight is still moving at exactly the speed of light from your perspective. Not a fraction faster, just light speed. 299,792,458 meters per second, precisely. Now here's the part that should make you uncomfortable. The person on the train measures the same light beam. From their perspective, they're standing still. They shine the flashlight, they measure the speed, and they get exactly the speed of light. Same number, same speed. You both measured the same beam of light. You're moving relative to each other at half the speed of light. That's 150 million meters per second relative velocity. And you both got the same answer. That's impossible. That breaks mathematics. If you're moving at different speeds, you have to measure different speeds for the same object. That's how velocity works. But light doesn't care about your mathematics. Light doesn't care that this seems impossible. Light does it anyway, every time, without exception. And when something in nature consistently violates what seems like basic logic, it means your logic is wrong, not nature. Your assumptions about reality are fundamentally incorrect. And here's what Feynman understood that most people miss. The speed of light isn't the barrier. The speed of light is the symptom. The real barrier is something far more fundamental, something built into the structure of existence itself. Let me show you what that means. Start with something simple. Something you're doing right now. You're sitting in a chair, or standing, or lying down. Whatever you're doing, you think you're not moving. You're just there. Still. At rest. Stationary. Zero velocity. But you're wrong. Completely wrong. You're moving right now at the maximum possible speed through the universe. Full speed. Flat out. As fast as anything can possibly go. Maximum velocity. You're just not moving through space. You're moving through time. Every second you move 1 second into the future. Tick. 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 That's motion. Real motion through a real dimension. Time is not some abstract thing that just happens. Time is a dimension, a direction you can move in. Just like space, you move through it continuously, 1 second per second. That's your speed through time. And here's what almost nobody realizes, that's the maximum speed. You're already going as fast as you can go. Right now, sitting there, you're maxed out. Now you stand up, you start walking, maybe you start running. You're now moving through space, 3 miles per hour, 6 miles per hour, whatever. But here's the thing that should blow your mind. Your total speed through space-time hasn't changed. You're still moving at the same maximum rate, the same speed you had when you were sitting still. But now some of that motion is through space, which means less of it can be through time. You're moving through time more slowly. Your clock is ticking slower. Not metaphorically, not approximately. Literally. Time itself is passing more slowly for you than for someone sitting still. This is real. This is measured. This is not philosophy. Atomic clocks on airplanes tick slower than atomic clocks on the ground. They don't tick slower because of vibration or temperature or measurement error. They tick slower because less time is actually passing for them, by exactly the amount Einstein's equations predict, to the nanosecond. We're talking billionths of a second here, but it's measurable. It's real. It's there. The Haefel-Keating experiment in 1971. They took 4 atomic clocks on commercial airlines, flew them around the world, east and west, compared them to atomic clocks that stayed on the ground. The flying clocks lost time, not because they were broken, because they were moving. Because when you move through space, you move through time more slowly. The faster you move through space, the slower you move through time. This is not optional. This is not a theory that might be wrong. This is tested, confirmed. Used in technology you depend on every single day. And there's a limit, a hard limit. If you move through space at the maximum rate, you have zero motion left for time. Time stops. Completely. Zero time passes. That maximum rate through space is what we call the speed of light. 299,792,458 meters per second. Light moves through space at the maximum possible rate, which means it has zero motion through time. From a photon's perspective, no time passes. Ever. A photon emitted from a star a billion light-years away experiences zero time between emission and absorption. From its perspective, the journey is instantaneous. Not fast, instantaneous. Zero elapsed time. The entire history of the universe, billions of years, happens in zero time for a photon. Think about that. A photon sees the Big Bang and the heat death of the universe in the same instant. Its entire existence is one eternal now. Now here's where it gets strange. You might think, okay, so if I'm moving through space and time at a fixed total rate, what's stopping me from shifting more motion into space? Can't I just keep accelerating? And the answer is, you can. You can keep shifting more motion into space. But as you do, something happens. You become harder to accelerate. Your inertia increases. We call this relativistic mass, but that's misleading. Your mass doesn't really increase. What increases is your resistance to further acceleration. And here's why. When you're moving close to the speed of light, you've already used up almost all your available motion through space-time. You've shifted nearly everything into spatial motion. There's almost nothing left. Trying to go faster is like trying to squeeze water from a dry sponge. At 99% the speed of light, you're using 99% of your motion budget for space. Only 1% left for time. To go from 99 to 99.9% requires enormous energy because you're trying to reallocate that last tiny bit. And to actually reach 100% would require reallocating the last infinitesimal fraction of temporal motion. That requires infinite energy. Actually infinite. Not hyperbole. It's not possible. Not with any amount of fuel. Not with the energy of the entire universe. Because the geometry of spacetime makes it meaningless. You can't have negative motion through time. Zero is the limit, the hard floor. And zero motion through time corresponds to moving at the speed of light through space. You can get arbitrarily close, 99.99999%, but you can never quite reach 100. The universe won't let you. This is what Feynman meant when he said you can't go faster than light. It's not that light is special. It's that space-time has a structure, a geometry, and that geometry has a built-in exchange rate between space and time. We call that exchange rate the speed of light, but that's historical accident. It should be called the space-time conversion constant, or the maximum rate of causality, or the speed at which now propagates through the universe. Light travels at that speed because photons have no mass. Zero mass means zero resistance to motion. They move at the maximum rate automatically, not because they're trying, because they have no choice. But the speed itself has nothing to do with light. If light didn't exist, the speed limit would still be there. It's a property of space-time, not of photons. Now you might ask, why? Why is space-time structured this way? Why is there a conversion factor at all? And here's the answer that's probably not going to satisfy you. There isn't a deeper why. That's just what space-time is. Asking why space-time has this structure is like asking why space has 3 dimensions. It just does. That's the universe we're in. We can describe the structure mathematically. We can make predictions. We can test them. And every test confirms it. But we can't explain why the universe has this structure rather than some other structure. That's not a physics question. That's philosophy, or theology, or both. What we can do is figure out the consequences, and the consequences are wild. Time dilation isn't some weird edge case, some exotic phenomenon that only happens in particle accelerators or near black holes. It's happening right now, everywhere, all the time. You and I are experiencing time at slightly different rates depending on our motion and our position in Earth's gravitational field. Right now. As you read this, Your head is experiencing time slightly faster than your feet because your head is slightly farther from Earth's center. The difference is tiny, impossibly tiny, but it's real. It's there. GPS satellites have to account for this. They have to account for time dilation from two different sources. First, they're moving fast, about 14,000 kilometers per hour relative to the ground. That makes their clocks run slower. Time dilation from velocity. But second, they're also higher up in Earth's gravitational well, about 20,000 kilometers above the surface. That makes their clocks run faster. Time dilation from gravity. General relativity, not special relativity. These two effects work in opposite directions. The velocity effect slows their clocks down. The gravitational effect speeds them up. The gravitational effect wins. It's larger. Net result, GPS satellite clocks run about 38 microseconds per day faster than clocks on the ground. 38 microseconds. That's 38 millionths of a second. Sounds small, but GPS works by measuring the time it takes radio signals to travel from satellites to your phone. Radio signals travel at the speed of light. The speed of light is about 300,000 kilometers per second. In 38 microseconds, light travels about 11 kilometers. 11 kilometers is 7 miles. If GPS didn't correct for relativity, your position would be wrong by 7 miles after one day. After a week, you'd be off by 50 miles. The system wouldn't work. It would be useless. Every GPS satellite is a tiny relativity experiment happening in real time, proving Einstein right billions of times per day. Every time you check your location, every time you navigate somewhere, you're depending on relativity being correct. Particle accelerators push this even further. The Large Hadron Collider accelerates protons to 99.999991% the speed of light. 7 nines. That's fast. Absurdly fast. At that speed, the protons are experiencing time almost 7,000 times slower than we are. For every second that passes for us, only about 0.14 milliseconds pass for them. And the closer these particles get to light speed, the harder it becomes to accelerate them further. Exactly as predicted, not approximately. Exactly. To the decimal point. You can pump more and more energy into them. They gain energy. Their momentum increases, but their speed barely changes. Going from 6 nines to 7 nines. From 99.9999 to 99.99999. That takes enormous energy. Going to 8 nines would take even more. 9 nines, even more still. You can keep going, but you never reach 100%. The universe won't let you. The equations work, the predictions match, every single time. Cosmic rays from space create particles called muons in the upper atmosphere, about 15 kilometers up, high altitude. These muons are unstable, radioactive. They decay. They have a half-life of about 2.2 microseconds, 2 millionths of a second. That's not long. At the speed these muons are traveling, about 99.98% the speed of light, they should travel about 660 meters before half of them decay. 660 meters. That's less than 1 kilometer. They're created 15 kilometers up. They should all decay long before reaching the ground. Maybe 1 in a trillion might make it. Maybe? Statistical fluke. But they don't. They reach the ground. Lots of them. About 1 muon per square centimeter per minute at sea level. We can measure them. We can detect them. They're there, hitting the ground. So what's happening? How are they getting here if they should have decayed? Because they're moving so fast that time slows down for them. From their perspective, from the muon's reference frame, they live 2.2 microseconds. That's their proper time, their wristwatch. But from our perspective, from Earth's reference frame, they live much longer, about 50 microseconds, 20 times longer, because their clocks are running slow. Time dilation. At 99.98% light speed, time dilates by a factor of about 15 to 20, depending on exact velocity. From their perspective, they travel 660 meters before decaying. But the distance is contracted. Length contraction. Another relativistic effect. From their frame, Earth is rushing toward them at near light speed. And when something moves that fast, distances contract in the direction of motion. Earth isn't 15 kilometers away from their perspective. It's less than 1 kilometer away, about 700 meters. So they travel 660 meters in their lifetime and cover 700 meters of contracted distance. Some make it, some don't. Works out. From our perspective, they travel 15 kilometers in 50 microseconds. 15 kilometers. Time dilation. They live longer because they're moving fast. Either way you calculate it, from the muon's frame or from ours, you get the same result. More muons reach the ground than classical physics predicts. Many more. Relativity predicts the exact number, and when we measure, relativity is right, every single time. This has been tested over and over since the 1940s. Carl Anderson, the muon experiment. It works, it's real, it's not theoretical. You can do this experiment yourself with the right equipment. People do. Physics students, undergrads, they measure cosmic ray muons at different altitudes, ground level, mountain tops, compare the numbers, see time dilation directly, see relativity in action. Here's what all this means, what it really means. The universe is not what you think it is. Space is not a fixed stage where events happen, some unchanging backdrop, some container that holds things. Space is dynamic. It bends, it warps, it stretches. Time is not a universal clock ticking the same for everyone, some absolute metronome keeping beat for the cosmos. Time is relative. It depends on your motion. It depends on gravity. It runs at different rates in different places. Space and time are relative. They're flexible. They bend and flex and stretch to accommodate something absolute. The speed of light, or rather, the maximum rate of causality. The speed at which now spreads through the cosmos. The speed at which information propagates. You can't outrun now. You can't go faster than cause and effect. You can't violate causality. That's the real barrier, not the speed of light. Causality itself. The structure of space-time enforces this. It's built in. It's fundamental. You want to go faster than light? Fine. Think about what that means. That means going backwards in time. That means effects preceding causes. That means receiving a message before it was sent. That means reading a book before it was written. That means dying before you were born. That means shooting yourself yesterday. Paradoxes, contradictions, logical impossibilities. The universe doesn't allow it. Not because of some arbitrary rule. Not because some cosmic cop will pull you over. Because the geometry doesn't permit it. The mathematics doesn't work. It's not forbidden. It's incoherent. It's like asking what's north of the North Pole. The question sounds reasonable. The words are all English. The grammar is correct. But the question doesn't make sense. There is no north of the North Pole. North is defined as the direction toward the North Pole. When you're at the North Pole, every direction is south. North doesn't exist there. Similarly, there is no faster than the maximum rate of causality. The words sound like they mean something. Faster, than, light, speed. All words we understand. But put together in that way, describing that concept, they don't refer to anything real. They're grammatically correct nonsense, verbal noise. And this is the thing about deep physics, the thing that separates it from everyday experience. The deeper you go, the more you realize that common sense is just a local approximation. It works at human speeds. Walking, running, driving, flying, human scales, meters, kilometers, miles, human situations, normal gravity, normal temperatures, normal conditions. But it's not fundamental. It's not the deep truth. It's a useful approximation in a limited domain. At high speeds, at small scales, at extreme conditions, reality works differently. Not sort of differently. Not a little bit differently. Fundamentally differently. The rules change. The logic changes. Time is not absolute. Space is not fixed. Simultaneity is relative. Your now is not the same as my now if we're moving relative to each other. We don't share the same present moment. There's no universal present, no cosmic now. The universe doesn't have a clock, doesn't have a calendar. Different observers slice space-time into space and time differently. Your space is tilted relative to mine. Your time axis points in a different direction than mine. We're experiencing different presents, living in different nows. And somehow, despite all this relativity, despite all this flexibility, despite all this chaos, one thing stays constant. Always. Invariant. The same for everyone. The speed of light. The maximum rate of causality. The conversion factor between space and time. That's the anchor. That's the thing that doesn't change. That's the fixed point around which everything else rotates. Everything else, time, space, simultaneity, all of it flexes and bends to keep that one thing constant. Always the same. Always invariant. Feynman understood this. He spent years teaching it, explaining it, finding new ways to make people understand, new analogies, new thought experiments, new angles. He taught at Caltech for decades. His lectures became legendary. The Feynman Lectures on Physics, 3 volumes, still in print, still used. Because he had a gift. He could take the most abstract, most mathematical, most counterintuitive concepts in physics and make them clear. Not simple, clear. There's a difference. He didn't dumb it down. He didn't pretend it was easy. He showed you the depth, the strangeness, the beauty, and his insight was this. Don't think of the speed of light as a speed limit imposed on objects. Don't think of it as a rule, a law, something external, something restricting you. Think of it as a structural feature of space-time itself, intrinsic, built-in, fundamental. The speed of light is the speed of space-time. It's not a speed through space-time. It's the speed at which space-time propagates. The rate at which the universe updates. The bandwidth of reality. The clock speed of existence. And once you see it that way, the question changes. The whole framing shifts. You stop asking, why can't we go faster than light? That's the wrong question. That question assumes light speed is some external limit, some barrier imposed from outside. You start asking, what does it mean that space-time has this structure? What does it tell us about the nature of reality? Why is reality built this way? And the answer, or at least part of it, is that space and time are not separate things. They're not two different entities that happen to coexist. They're aspects of a single thing, space-time, a 4-dimensional fabric, a unified structure with a particular geometry. A geometry that allows motion through time to be traded for motion through space. A geometry that connects them. That makes them interchangeable. That sets an exchange rate between them. A geometry that has a maximum rate built into it. Hardwired. Intrinsic. That maximum rate is what we call the speed of light. But it's deeper than light. It's more fundamental than photons. It's the speed of existence itself. It's the rate at which events can influence other events. It's the propagation speed of causality. It's the speed at which reality updates. It's the frame rate of the universe. And this, all of this, comes from one simple observation. One weird fact. One impossible thing. Light travels at the same speed for everyone. That one fact. That one contradictory, impossible logic-breaking fact forced Einstein to rebuild our understanding of space and time from the ground up. He couldn't keep both. He couldn't keep absolute time and absolute space and also keep the speed of light constant. Something had to give. And what gave was everything we thought we knew about space and time. What Einstein built in its place was more strange, more beautiful, more surprising than anyone expected. More radical, more revolutionary. Space and time as flexible, as relative, as observer-dependent, but connected, united, woven together into a single fabric with its own geometry, its own rules, its own logic. The speed of light isn't the barrier. The speed of light is the key. It's the thing that unlocks the true structure of reality. It's the thing that shows us how space and time really work. Not how we want them to work. Not how our intuition says they should work. How they actually work. And the fact that we figured this out, that humans figured this out, that we measured it, tested it, confirmed it over and over, that we can use it to build GPS systems and particle accelerators and understand cosmic rays, that we can make predictions and have them come true. That's extraordinary. That's astonishing. That's the power of physics, the power of science, not to make us comfortable, not to confirm our intuitions, not to tell us what we want to hear, but to show us how reality actually works. Even when, especially when, it's nothing like what we expected. That's the beauty. That's the achievement. We live in a strange universe, stranger than we imagined. But we can understand it. We can measure it. We can test it. We can know it. That's what Feynman saw. That's what he taught. That's what he wanted everyone to understand. The universe is comprehensible. Reality has rules. And when you find those rules, when you really understand them, they're beautiful. They're elegant. They're profound. The speed of light isn't just a number. It's not just a limit. It's a window into the deep structure of reality. And once you see through that window, you can never see the universe the same way again.